So let's build our first project here, and this one's going to be a really simple project. I'm just going to blink an LED, much the same as the blink project in Arduino. And even though it's simple, it's going to test a lot of stuff. It's going to test that we can actually edit a program or edit a source file. It'll test that the compiler is working properly, and it'll actually test that we can download the software to the microcontroller and that the microcontroller is actually working. So let's get started. The first thing we need to do is create the project. So bring up Atmel Studio as I've done here. Click on New Project, and it's going to be a GCC executable project, and change the name of it to Blink or whatever you want to call it. Browse into the directory where you want to put it, and then click this. So this normally is clicked here. You just want to create a directory for it, and then once you've done all this, just simply click OK. And next thing you have to do here is pick the processor. So let's go down to ATmega 328P, which is the one I'm using on my board. And now it's creating the project and the first source file. And the first source file, and in fact in this one it's so simple, the only source file will be called main. But you can see that it's given the name of the project is Blink. This is kind of odd here that they've given it the name Blink here but called it main. It doesn't really matter. It'll work. We could rename main if you wish, and it would probably work. It will work just fine. Now, just a bit of housekeeping to do here. It automatically included this, which is good. And what this library or header file .h file does is it creates definitions like the number sign define that I've talked about before for all of the registers and the bits in the registers for the microcontroller as they show up in the datasheet, so that it's easy for you to understand what's going on. The words actually mean something. So any project that you start up, you've got to make sure that you include this in the file. In fact, every source file, if you're getting into a project, we'll get into it later, not in this one, but in other projects where there's more than one source file, as I talked about in my second video, my previous video, each of those files will have to have this statement in there if you're going to be using any of the registers in the microcontroller. Now let's have a look at a schematic of the Arduino board, because I want to show you something about the microcontroller. So here is a schematic of the Arduino Uno. This is from Arduino themselves, and this is the ATmega 328, the microprocessor that you're going to be programming. Now, and these are the pin headers around the outside edge that have all the different pins that you can use for your projects. And you notice that they're numbered 0 through 7, 8, all the way up to 13. And then these are the analog ones. They're also labeled A0 through A5, I believe. Now, when you go to use an I/O pin under Arduino, you just give it this number, whatever it is, 10 or A5 or something like that. And then when you go to set up the I/O pin to make it an input or an output, and then to actually write to it, you use the functions pin mode and digital read or digital write. And those are functions, those are programs that Arduino has written, and it looks at the number that you give it of the pin, and then it sorts it out and figures out which I/O port of the microcontroller to use. Under Arduino, all the pins are just numbered in sequence from 0 to 13, but in the microcontroller they're done a lot differently, and you'll see that they're grouped here. And so you've got PB5, 5, 4, 3, 2, 1, and 0, PC, and then PD. So this is port C, or port B, port C, and port D. I don't know where port A went. I'm not sure why they didn't put a port A in there, but there's no port A. If you have a bigger microcontroller like an Arduino Mega, you'll have up to port F or G, I believe. I forget how many there are, but there's quite a few more I/O pins on the device. And they're all numbered in sequence as well. But the way the AVR chip does it is that it groups the pins in groups of 8. So even though there's not 8 in this PC or the PB, port C or port B, there are actually 8 potential port pins. Port B also shows up where the crystal is here as well. So these two, if you're not using an external crystal, you can use these as I/O pins as well. And they're port B 6 and 7. But Arduino doesn't use those. So anyways, when you access an I/O pin, you have to go to the appropriate port and the appropriate port number, PD7 for example. So what we're going to do here is we're going to toggle the or blink the LED that already exists on the board, which if you look around a bit you'll see it's this LED here. It's connected to ground through a resistor through this this driver. It's just I'm not sure exactly what it is. I think it's an op amp, but it's just like a transistor, and it switches this on and off. And you see this symbol here, S clock, goes all the way over to here to S clock. And if you follow it back, it goes into port pin B5. So we've got to toggle port pin B5 instead of using Arduino pin number 13. So that's how we're going to do it, is actually activate that appropriate pin in an appropriate register that drives port B. Now all 3 of these ports have 3 separate registers for each port. One register is called DDR, which stands for the data direction register. In it you set or clear bits in that register corresponding to the pins on here, to whether you want to make it an input or an output. Another register associated with each port is called PIN or pin, and that is when you read that port, it reads whatever the state is on this pin, whether it's a high or a low. And the third register is called port something, port B, and when you write to that, you actually write to the I/O pin here. So you write a 1 to this pin, it will go high. You write a 0 to this pin, it will go low. Sounds complicated, but once you understand how it works, it's actually not too bad. And now on my board that I'm going to use, which is not an Arduino board, it's made by another company. It's quite similar, except there's no driver in between the LED and the port, but it does go to the same port, port B5. So we'll be using that pin to drive that LED to blink it on and off every whatever half second or something like that. Alright, let's have a look at the ATmega 328 datasheet. Or data, yeah, it's called a datasheet. It's not a sheet, it's like 448 pages long. There's quite a lot of information in here, but once you start digging into it, it's not that hard to deal with. I'm just going to look at one specific area called the I/O ports, and it just describes how the I/O ports are made up. You can see some pictures here. Let's look at the, well, let's go directly to what I want to look at, which is the registers. So these are the 3 registers for the port B. The port data register, which when you write to it, it sets the I/O pins high or low. This is the data direction register, and this is the input register. When you read that one, you get your pins. This other register up here, I'm not going to worry about. So here is the description of all these registers, and you can see how they correspond to the pins as well. The low order, or the least significant bit, is down here. The most significant bit is up here, and these correspond in the same order to the pins on that port. Now port B doesn't have all of the, well, it does have actually these 2 pins as well, but they're used up on the Arduino board for the crystal, and so they're not actually available as I/O pins. We go to port C down here. As you can see, they've blanked out this one here because port C7 doesn't exist. It's just not implemented physically. and we go down to port D, and it has all of them here. And but these are the registers that I just talked about already, and even gives the address of where they're located in the memory system of the microcontroller. So we'll be going into the datasheet more than once. For each peripheral that I'll talk about, we're going to go into the datasheet for that peripheral and look at the different registers and learn how to control the bits in those registers to make the peripheral do what we want to do. But this is just a quick look at the I/O ports. So back here in AVR Studio or Atmel Studio, let's start writing some code. Now the only function we're going to work with here is main. Remember what I said in my previous video, that main is automatically called right after power up, after the microcontroller is reset or after it's powered up. And so you have to do all your initialization at the beginning of main here before it goes into the loop here where you're actually doing something. So we're going to have to initialize the I/O port to make that pin an output, and then in here we're just going to toggle the pin and delay, and then toggle means change the state of the pin, and then delay and change the state of the pin again, and delay, etc., etc. It's just going to stay in this loop forever, blinking that LED on and off. Now we looked it up and we saw that the LED was on port B pin 5. So we have to change the direction of that pin from an input to an output. And so we go to DDR-B, and that's the register that we have to modify in order to get that I/O pin to be an output. And you notice the color, it came up with a different color here. And one thing about Atmel Studio is it's got quite a lot of useful features, and one of the main features is this visual assistant. And if you've got a constant like this thing here, you can click on it and then it shows up here what it's defined as. So in this file here, you will find a statement that says this. Now I want to make that pin, or I want the bit 5 in that register to be a 1, because when the bit is 1, that corresponding pin is an output. When the bit is 0, that corresponding pin is an input. So there's a number of ways we could do this. I could just brute force it and make it equal to, and I'll write a binary notation. So we go 0B, that tells me, or tells the compiler, that the following information after 0B is all in binary, so it's just ones and zeros. And we're going to, since this register is only 8 bits wide, we need to only put down 8 bits here. So I'll put down first of all 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So what that'll do, that statement there will do, is we'll write all zeros into that register. But of course we don't want them to be zeros, because we don't want them all to be inputs. We want to make port B5, pin 5, an input. So I have to, or an output, sorry. So I have to make that one 5. Now the order of the pins is, the least significant ones are down at this end here, which is bit 0, and then it just goes up bit 1, bit 2, 3, 4, 5, 6, and bit 7. Now which is also port pin 7, or port. So we go down to pin, 5, so 7, 6, 5. So we've got to modify this one here, and we make that a 1. And so we can write that directly to that register, and that will make all of the I/O pins except for pin 5 inputs, and then we make pin 5 an output. Now there's a problem here, that if you've got, well, should I get into it now or not? I'll set the idea up here and we'll look at it in more detail later, because we're going to see it later on in the code here. But this modifies all of the bits in that register at the same time. And maybe you've got one bit that you want to modify but not all the other bits, and there's a better way to do it than this, but for now we'll just do it this way. So now I've set up port B pin 5 to an output. Now in order to make the LED turn on, I have to write a 1 to that pin. Remember I explained that of the 3 registers for that port, it's port the port register, the port B register you write to make the I/O pin go high or low. So we write port B, and the same thing we can do equals, and we'll do our binary notation here again. 1, 2, 3, 4, 5, 6, 7, 8. And then it's pin 5, we want to make it high, so we'll go to pin 5 and make it 1. Now if we want to turn that LED off, we just simply do the same thing, except we make that pin low. So we go port B equals 0 B, and then in this case all of them are 0. Now we could compile this and download it, and it'll run. It'll blink the LED on and off. It'll just do it really fast. And so we want to be able to see it blinking on and off. And so we need to put a delay in between each of these. So we're going to have to put a delay of some sort in here, and then another delay in here. And I should explain a little more carefully here what's going on in this while loop. You see between these two curly brackets that are now highlighted, the processor will execute all the code in here, and it will execute it one step at a time until it gets to the bottom curly bracket, then it jumps back up to the top curly bracket and continues again. And it'll do this forever and ever and ever until you turn off the microcontroller. And the compiler will make code for this particular statement, and it actually compiles to a single instruction. Same with this one. And a single instruction will operate at the full speed of the microcontroller. Now, on the Arduino boards, the microcontrollers are running at 16 megahertz. So if you so at 16 megahertz, it's executing one instruction at 16 megahertz. So if you do some calculations, 16 megahertz, and you figure out how many seconds that is per instruction, that's 62.5 nanoseconds per instruction. A nanosecond is 10 to the minus 9 seconds. It's less than a microsecond. And so it's going to take no time at all, as far as humans are concerned, to execute this program. So we need to put a delay in here. Now the compiler comes with a built-in delay function, and it's called _delay _ms, which stands for milliseconds. And then you put a parameter in here of how many milliseconds you want it to delay for. And I'll fill that in a moment, and we'll do this again down here. So we have our two delays. Now the compiler is not going to be able to find the delay function. It's not defined. Actually, maybe it is somewhere. Actually, it may be already defined in here. Let's see what happens if I don't include it. So anyways, let's see how long we want these to delay for. Say we want it to blink on and off. You want it to be on for a quarter of a second and off for a quarter of a second. So 250 milliseconds we'll put in here. And I forget how many, I forget what the maximum is. Delay milliseconds has a limit. I'm not sure how many it is. I think it's more than 250 milliseconds, but we'll leave it at that. So now the program is written. We have set up our I/O pin to be an output in this instruction. We make the I/O pin high with this instruction. We delay for 250 milliseconds, or a quarter of a second, with this one. Set the output pin, or the port B pin 5 to 0 to low, turns off the LED, and then we delay for 250 milliseconds, and then we go back around and we start all over again, and we just do this over and over and over again. So that's our program. Very, very simple, and it's going to compile into some very small amount of code. So let's build it. So this is the button that you click for building it. We'll click on that. A bunch of output comes out down here at the bottom. So it didn't like that. There was an error. So it could not find delay milliseconds. That's because I didn't include a header file. So let's put that in there. Number sign include and I prefer to do it this way, and it's util /delay.h. Now we can save this file. You'll see up here that this little asterisk, this indicates that the file has been changed but not saved to disk, and this is the button you click to change the current file. If you've had more than one file across the top here and more than one file that was open and unsaved, you can click this button here and it saves all the files. But we'll click this one to save it. If you're going to compile right away, it doesn't matter. When you click on the compile button or the build button, it will save all the files before it starts building. So let's do this again. And there we go. Now it has another error. I forgot to mention this. There is a constant that you have to define called fCPU, and it gets used all over the place. And it defines what the oscillator frequency of your microcontroller is. So I'll put that down here, $ define. So you can, oh, here's something I forgot to talk about with the virtual assistant. You see that I've typed the first couple of letters of a word or something, and this little stuff here pops up, and you see that this $ define in this little box is highlighted. So I don't have to continue typing define. I simply hit the tab key and it completes it for me. This is part of the virtual assistant. As you play with this, you'll start seeing how it helps you out. So we need to put in f_CPU, and I'm running mine as an Arduino board, so it's going to be 16 megahertz in it. 3, 4, 5, 6, and that's the definition of our frequency of our microcontroller, 16 megahertz. It's written in hertz. Generally, you want to, because it's such a large number, you want to tell the compiler to treat it as a big number, and so you usually append to the end of these numbers UL, which stands for unsigned long. Long is a 4-byte number, which is, if you work it out, 2 to the 32, 2 raised to the 32nd power is a huge number. And anyways, the 16 million will be contained in that that word of 32 bits or 4 bytes. Okay, now that's our definition done here. Let's recompile it again. Don't have to save it because it'll save automatically when I start the compiler. And fCPU is redefined. Where is it defined? Oh, I know where it's defined. Okay, here's a trick. We go to our Solution Explorer and click on our project Blink, right click and go down to Properties. Now I can't put any of this stuff up onto my cloud-based where you can download the code here, so you'll have to follow this along in the video here. So this brings up the project properties, and I'm going to go down to Toolchain. Toolchain is just the programs that compile your software. We need to go down to the GNU C compiler and go to the preprocessor. Oops, sorry, symbols. Oh, where is it defined? Trying to figure out where fCPU is defined, predefined. Well, we can put it in here, and let's see what happens when I do that. Oh, I know what. Okay, if we look down here again, I misread this. fCPU is not defined for the util delay library. That's the reason. So what we're going to do here is, I can't go to the util delay files and put in fCPU. I have to do kind of a global fCPU definition, and this is where you do it. So you go to the tool chains under the project directory or the project properties, C compiler symbols, and I'm going to define a symbol by doing this. I click on that, I'm going to add a symbol, and I'm going to add underscore CPU equals 1, 6, 1, 2, 3, 4, 5, 6 UL. Now what I've done here is I've defined a symbol called fCPU that will be used in any source file that you compile. So if you've got more than one source file that needs fCPU, it will automatically be included in your when you compile, and you don't have to write it into every file that you create. So let's save the properties, get rid of this, and recompile, and I think we're going to work just fine. There we go. Build succeeded. In fact, I can get rid of that right now. Let's recompile it, and it should be fine. Yeah. So let's scroll up a little bit here, and we can have a look at how much program memory used. 178 bytes. Now, there wasn't too many bytes used here, but there is some code that executes prior to main starting up, and it just sets up some of the variables. All right, let's hook up the board to the programmer. So the port you're going to be plugging the programmer into is this port here, and you notice that there's the pin 1 is marked with a 1 right there, and the programmer pin is, or the programmer socket or plug is this guy, and if you look at it, pin 1 is this one right here. So you just plug it in like this. Now, a little hard to do on camera. There we go. Microcontroller, or the programmer, is now plugged in. I'm just going to spin it around this way and then plug in the power to it. And these lights should come on as shown here. I don't know if they show up too well on the camera. There, that's better. The red and the green should be on. Now, I'm not plugging my Arduino board into the USB port. As you can see here, I've powered it externally with I've got a 9-volt DC adapter that I plug into this, and it powers it quite nicely. You could plug it in to the USB port to power it that way if you wish. It doesn't affect the programming. I just don't have any USB ports available right now because I'm using them up for other things. And anyways, that's how it's hooked up, and then we'll go back to the monitor, the computer, and show you how to start the programmer. And we're ready to program our microcontroller. And we look for this button here, which has got a chip with a lightning bolt through it. That's our programmer. And then just double check that you've selected, or it has selected, the correct microcontroller. And off screen here, I changed mine to the ATmega 3228 without the P, because I didn't have any with the P versions. Not a big deal to change it. Anyways, bring up this window, check that you got the right microcontroller in here and the right tool. I'm using the Atmel Ice, and then you hit apply, and it just sets up the communications. And if you want to check that it's actually talking to the microcontroller, you can hit this read button, which is reads the device signature. It came up without any errors, and that's good. So we are set up here to program it. Now, you may have heard of the fuse bits that the microcontroller has, and these are bits that control the personality of the microcontroller, but they are not programmable using the bootloader. So you're not able to program them under Arduino, and you have to use an external programmer that I've got here. Now, if you're using a brand new chip from Atmel, it will come from the factory with some of the fuse bits programmed in a way, and it won't work in your board. The microcontrollers come with a built-in oscillator, and it runs at 8 megahertz, and the fuse bits are set up so that it's running off of that oscillator instead of the external crystal that is on the Arduino boards. And so that's one thing that you'll have to change if you're using a brand new microcontroller. And so you've got to also be very cautious with fuses. You can unprogram one of the fuses, and then it makes the device not programmable with these basic external programmers, and you got to get a special high voltage programmer in order to reburn that fuse so that you can actually program it with this kind of a programmer. And so I'm just going to show you what the fuses look like. So you hit that button, it reads all the fuses. You don't want to change any of these things, especially this one here. This is called the serial programming enable. If you disable this, then you can't program it either with well, you could probably program it with a bootloader, but you can't program it with the external programmer that I'm using. But we'll scroll down, and what we've got here is, so this is a brand new chip that I've just plugged in. So the This fuse set is set to the internal RC oscillator, 8 megahertz, and then there's a startup time, which you don't have to worry about. I just program it to the longest startup time. If you click on this, it brings up all the different options. This option is just fine. You don't have to change it. But what we need to do here is change this to external crystal. Let's see, external crystal 16 megahertz. 16. I gotta look at this again. External oscillator. Okay. I'm gonna have to look this up to see which one we're supposed to set it to. I believe. Okay, so here we are back again. I had to look it up. What we're looking for here is the crystal oscillator, or external crystal oscillator, and this means 8 megahertz and up. And we're looking for a startup time of 4.1 milliseconds, and so we'll click on that. And we haven't programmed it yet, that's why it's got this here. Now, I don't want the 8 megahertz oscillator divided by 8, so we have a 1 megahertz main CPU frequency. I want it to run at a full 8 megahertz, so I unselect this and then I program those pins. Boom. Gives you a warning. And there we go. So now it should run on the Arduino board. Now let's go back to memories, because that's what we're going to program next. Now the Atmel Studio has already picked the proper file here. It's the blink.elf file. You could also pick the blink.hex file and it would work as well, but the elf file just contains more information. And that's the file that we're going to read from and burn into our microcontroller. Now I'm going to try a picture-in-picture here, something I haven't done before. So let's turn my camera on. And I'm going to record as I'm programming it. So there it is. Now let's program it. Boom, it's done. And if everything works, there should be a blinking light on the board, and definitely there is. The green or the blue LED here is blinking on and off. So we were successful in editing the program, and we were successful in compiling it, and we were successful in the programming it, with the programmer communicating to the chip and programming it properly. So that is all for now for this one, a very simple Blink program. I'm not going to bother posting this code up onto my GitHub site. You guys can read this directly off the screen. It's not that complicated to write it down. In my next video, I'm going to play around with I/O ports and more LEDs, and I'm going to show you a nifty way of controlling a number of LEDs with the minimum number of I/O ports. Kind of a cool thing to do. Anyways, hope you enjoyed it. Stick around for the next one.